up, everyone. Last week we had our session on maths with Ash, and today we have Carl on our show called Carl Connect Physics in Daily Life. Linsha, can you please introduce our speaker for today?
Hi everyone, I'm Linsha from Science DD, and our speaker today, Carl. Carl is a physics teacher and he has been an educator since 7 years. So he has taught design, technology, coding, math. He loves physics. So and also he's running Science Hub and Math Jam. Carl, can you tell more about this?
Of course I can. All right, so hello everyone. So I run Science Hub and Maths Jam. So Science Hub is basically to promote science in the general public. We have done public demonstrations of different experiments to give people an idea of what science is and how it's done. We have also conducted a few public talks. Because I'm from a physics background, I usually handle the physics side, and we also want the members who are from science background to also be a part of the community and share their knowledge. In Maths Jam, I run the Mumbai chapter of Maths Jam, where we actually get people to come and solve puzzles. Okay, it's not just maths, so it's mostly puzzle. And my stream has gone. All right, so should we start with today's session?
Yeah.
Okay. All right. So we are starting with. So today we're going to talk more on physics in daily life. So where do physics come? Where do you see physics in day-to-day life? And I thought, like, since monsoons is going on, we'll focus on rainbows first. So can you just bring up the slide?
Yeah.
Thank you. All right. So in rainbows, everyone knows, everyone has seen rainbows. Hopefully everyone has seen rainbows at least some point in their life. And it's a very beautiful thing that you can see in the sky wherever it's... Sorry?
I've seen a double rainbow.
You've seen a double rainbow. Okay. So although it looks very pretty and it looks in the sky, you normally see this only at very specific time of the day and in a very specific condition. For first, like, you need the rains. You don't see rainbows during summer unless it rains in summer. But mostly these rainbows happen because of something we call it as refraction. When light actually changes medium, it kind of splits into its component colors, and that's how we see the rainbows. And the splitting is done by raindrops. There are more than one thing happening over there. You'll notice that right at the start, the light, when it enters the raindrops, it already starts splitting, but it has to reflect and come back. So all of these effects that play together in physics actually creates a rainbow. Now, few things that most people don't know is that whenever you're watching a rainbow, if you look at the image, the sun has to be behind you. You cannot be facing the sun and expecting to see a rainbow. All right. Mm-hmm. And second is that whenever you look up into the sky, the rainbow is at a certain angle. So as the sun is rising in the morning, let's say, after a certain time, after 10 o'clock, you will not be able to see the rainbow at all, because even though the rainbow might form, it might not reach your eyes. So the best time to see a rainbow is early in the morning or late in the evening. And you need to be facing away from the sun in the direction where there is rain that's falling. So you need sunlight, rain, and the right angle and orientation, and the right timing. All right. So one more thing that I noticed about the rainbow is, and you said like you saw the double rainbow, right? So
yeah. So if you can tell us a bit about double rainbows.
So double rainbows, right? Okay. But so if you notice in this image, there's a raindrop over here, and like the light which is entering the raindrop is actually splitting the light into different colors. But what it also does is the light gets trapped in the bubble of the raindrop, and it kind of keeps on bouncing around multiple times, creating multiple rainbows. So the first rainbow is the brightest, and that's what you see. Okay. Right. The second rainbow actually forms behind you, and you won't be able to see it because if you turn around, you will see the bright sun over there. So you can't see the second rainbow. In a double rainbow, what you see is the first rainbow and the third rainbow. So if the sky is clear enough, if the rain is just right, if it's too rainy, you will still not be able to see the rainbow because you can't see through the rain. Like it just scatters the light around. It has to kind of drizzle and have a mist over there. All right. So usually, if you have seen a double rainbow, if you ever remember seeing a double rainbow, it's going to be more of a clear sky rather than like a heavy rain sort of a thing. And yeah, I don't have an image of a double rainbow. One peculiarity you see in the double rainbow is that while looking from the ground upwards, you will see violet, indigo, blue, green, yellow, orange, red. But in the second rainbow, the color inverts. So it goes red, orange, up to violet. It goes the other way. All right. And notice this next time if you ever go out and if you ever observing a rainbow, you will see that these both rainbows are inverted to each other. Not just that, another thing you'll notice is below the rainbow, the sky is brighter, while above the rainbow, the sky is dark. And the reason why that happens is because all these raindrops on top of the rainbow, which is there, it's kind of reflecting the light in different direction and not towards you. Okay, so that light is not coming towards you, making the sky dark. Whereas all the raindrops below the rainbow, even if it is reflecting the light away from you, the raindrops ahead will scatter somewhat towards you, making it kind of bright. It's a simple explanation. From a physics standpoint, there's a lot going on over here. Okay. Another thing is that yes, it's a double rainbow. You'll notice that below the first rainbow, the primary rainbow, the main one, the sky is much more brighter. And and between the two rainbows, the darkest.
The colors
are inverted.
Yeah. So the red is starting. The first rainbow is starting with red, and the outer rainbow, which is lighter, you cannot see it very well. It's actually red in the bottom. Yeah. This is what I've seen. I was on a train one day and I just saw this.
Also, you notice like the sky is more clear. You can't see the rain because the rain is quite far away from you. It's not raining where you are there. You can also see the sunlight. And if you notice from the shadow, the sun is actually behind you.
Yeah, definitely. Okay.
So these are the conditions that you require. You can't, if you have good sunglasses, if you are wearing good sunglasses, sometimes they are polarized. And they might cancel out the light of the rainbow. So even if you look at the sky, you might not be able to see the rainbow. You might need to take out your glasses to actually see your rainbow. So if you're standing with a friend, your friend is wearing a sunglasses, you might be able to see it, while your friend will not be able to see it. Okay, because it's So the raindrops kind of manipulate the light in a certain way, like no.
Okay. On that note, we have a question. Carl, I'm sorry to interrupt, but Nikhilesh is asking a question. Is the part of the rainbow a section of the circle that we can see from a certain vantage point, or rainbows exist as arcs only?
So the rainbow actually can be a complete circle, but from your vantage point, because the rest of the rainbow forms below the horizon, like you won't be able to see it. If the earth was transparent, let's say perfectly transparent, you will be able to see the
circular rainbow. Okay.
Yeah. There are circular rainbows that you can see, but you have to see it from above, like if you're traveling in flight, and sometimes the plane actually tilts, you can see circular rainbow, complete circular. It's not a bow, it's a rain circle probably, if you want to call it.
Let me see if
you might find images of that. You'll find circular rainbows.
This image.
But these can only be seen from very high altitudes. You can't see it from the ground level, because from the ground level only the arcs are observed. Like you don't have enough visual range to see the entire rainbow. It gets cut off by the horizon.
Okay. So I think I pulled up one image. I'll just show this image before we move on to the next topic.
No problem.
Yeah, this is it. Yeah, this is what it will look like from a flight, you're saying.
Yes, so
above the ground. And it really looks like the person who's taken this is above ground. Yeah.
It is, and also you can see a double rainbow. In fact, it's a double circle. It's like extremely rare to see. The conditions are way too perfect for this to happen.
So basically, so I'll just try to summarize what I have learned about rainbows now. It's a prism. It's like the same effect that happens when a white light passes through a prism, and the light is breaking up into its component colors, right? And
Yeah.
because of the raindrops and the way the sunlight is hitting the light, the sunlight is coming towards the person who's viewing it. They're able to see it in different shapes and uh, uh, or even different numbers. That's right.
Yeah. Yes.
Okay. Okay. Tell us about more such physics phenomena, Carl.
All right. So I think that Newton was the first to actually study light using prism and make some theory about it. But people started studying, like splitting light into rainbows using prisms and looking at it in fine detail. And they found out that you don't see continuous rainbows with every light. Okay, if you glow gas, like the street lamps that you have, the neon, the sodium street lamps, the yellow lamps in the street, if you pass that, you will not get your entire rainbow. You'll get like one single yellow line, so to say. And what you see uh, by passing light through a prism depends on what is glowing, what is emitting the light. Okay, so you can use a prism to split the light which something is making to figure out what's there in the object. Basically, you can think of it like a fingerprint of the
Like
chemical that you're seeing.
like a
Yeah.
filter to see what the components of the light that we're passing on.
Yeah, so if you want, so in physics we call them, the technique is called spectroscopy. You basically make gas glow, pass the light through a prism, and then you see what lines you get, and it tells you like, okay, this has oxygen in it, or this has carbon in it. So the kind of lines that you get tells you what chemicals are present within that material that you're glowing. And so, a fun fact, the reason why I said that is because all of this started by trying to study the rainbow. And when people started studying the rainbow in detail, the sunlight in detail, they actually saw there are lines in the rainbow which told us what chemicals are there on the sun. And they could, we already knew from doing experiments on Earth what the fingerprints look like. So they looked at these fingerprints, checked it across the rainbow that we are getting from the sun, and we would say, oh, the sun has sodium, or the sun has oxygen, that way. And there was few lines which did not match any of the fingerprints, and that's when they realized that there is a chemical on the sun that we haven't discovered on Earth yet. Okay, this was a few decades ago, and they named this chemical helium because it was found on the sun first. Which sun? Like no, Helios was a nickname, Greek name for sun. So they called it helium. So helium is a chemical that was first discovered on sun, and then they later found it on Earth. So they found it through sunlight that there is a chemical that needs to be present having such a so-and-so fingerprint. So that I thought was a fun fact. The first time I actually heard it, I was
That's
like,
interesting.
really?
That's very interesting.
Sorry?
So basically, we are able to just by looking at the light fingerprint of each of the elements, you are able to say what element it is and not. That's very
Yeah, what element it is. The brightness of the light can tell you like how hot the object is. So whenever we say like there is like this star and it's this bright and this temperature and stuff, it's moving that fast. All of this thing is done by just looking at the rainbow. You look at the starlight, split it into the spectrum, and then look at which color is bright, which color is not bright, what lines are present, what lines are not present. And we can tell what the star is made of, how hot it is, whether it is moving away from us, towards us, and we can even tell how old the star is and how fast it's going to die. Like no, this when we say like the sun is 4.5 billion years old, how do we know that? It's because like the light gives us this information in some form. Okay, so I think we can go to the next topic. If do people have questions or like we can just go ahead, I guess. One of the topics that I would like to talk about is radios on cell phones. Okay, and yeah, I think so. Like this will just so the cell phones, they actually emit microwaves and they receive microwave. That's how communication happens. All right, and the antenna which you have, the size of the antenna depends on what kind of waves you actually send or receive. So waves basically are this. Okay, you have a hill and you have a valley. together is called the wavelength, right? And if the frequency is high, then the wavelength is small, which means you need a small antenna. If the frequency is low, the wavelength is high and the antenna is large. So with a cell phone, your Bluetooth works at a very high frequency, which means it can transfer data a lot, at a very high rate. But it also comes at a loss that you can't transfer the data very far. That's why Bluetooth is used for transferring data between computer and your cell phone, or between two cell phones. You can't send images and audio and video files across a long distance in meters and stuff. Your friend needs to be in your room if you're sending them images or files and stuff. Okay, but you can do it quite fast using Bluetooth. And because it can do it at that frequency, because the frequency is high, wavelength is small, the antenna is small. Radio, on the other hand, if you notice radio stations, they keep on saying 92.5, 84.1 FM. Those are the frequency in megahertz. And if you do the calculation, the wavelength comes out to be in 1 meter length, or 75 centimeters, which is like almost a meter length. Like, it's quite long. And you can't fit that long of an antenna inside the cell phone, which is of this size.
Yeah.
So what you need to do is, like, you need to plug in the headphones, and the electronics within the headphones, the electron within the cell phones can use the headphones as the antenna itself. So if you unplug the earphones, you can't get radio on your cell phones. You can do communication, because talking to someone uses a different frequency, and the antenna for that is inside the cell phone. If you open your battery and remove it, you'll see a metal plate inside. That's basically the antenna of the cell phone, and it's of that particular size because it uses a certain particular frequency. There are other things. So, like, we know how to design cell phones because we know how the physics of radio waves and microwaves, how they work. And there is a lot more physics within cell phones when it comes to how the batteries are used, than how the electronics works within it. In fact, one of the main things that I like is the cell phones are small because we use something called as transistors, right? And these transistors were only invented about 35 years ago. Like, the prototype, the first transistor, was somewhere around 1970s, 1975, I think so, slightly around that area. And it was huge. Like, it used to, like, fit on a table. But nowadays, in your computer microprocessors, you have millions and billions, probably. I'm not sure how many, but it's in 6-digit zeros. So about more than a million, or more than a billion, like, transistors in very small area. And that's how we actually get our cell phones and our computers to actually work that fast and work that well. So that is one thing that I. Okay.
So basically, these are different radio waves, Bluetooth, light itself. All of these are different types of waves that are there.
Yes. So they're called as electromagnetic waves.
Yeah.
They're called as electromagnetic waves in general. And when I talk and when someone else talks, and you're talking and I'm talking, the sound sounds different because there are different frequencies within it. So the frequency is low, you will have a high, like, lower pitch. It's going to sound more bassy, like drums and stuff. But if the frequency is high, it's going to sound more sweet with a higher pitch, something like a flute. All right. And now, if you take the frequency way too high, there will be a point after which your ears will not be able to hear the sound. We call that ultrasonic sound, right? So dogs can hear some amount of ultrasonic sound. Okay. Bats use ultrasonic sound to actually move in the dark using echolocation. You all might know, like, bats make sound, it reflects from the object, they hear it, but that's ultrasonic. But when you go out in night and if you see bats around, you cannot hear any sound because your ears are not tuned to hear that particular frequency of sound. Same way, our eyes can only see a certain frequency of light. And if you make that frequency lower and lower and lower, it's going to become from blue to green to red. And after some time, the frequency becomes so low that you cannot see it. You go into infrared. And that's what your night vision goggles work on, like, thermal imaging works on. But you make the frequency even lower, this is still behind or beyond your capacity of seeing. we come into microwave. Okay, that range of frequencies called microwave. That's what your cell phone uses to communicate. Microwave is also the frequency you use to cook food in your microwave. That's why it's called a microwave oven. You know.
Yeah. So can you
Yeah.
explain us a little bit? I have a question. How does the microwave oven work? And how is it heating up my cell phone? It's the same thing.
Sorry. If how does it work, and what is the second question?
So it's the same wave that is being used in the microwave oven. So but it's not showing the same effect on my cell phone.
Yeah.
So
Okay, so first let me come to how the microwave oven works, and then we'll come to like how the microwave is different from the cell phone. All right. So you remember before I said that when you when you have a gas and you make it glow, it has a particular fingerprint, right? Like red light and green light, but it doesn't remain within the visible spectrum. It extends even in UV, and it extends even in radio waves and microwaves and stuff like that. Now, whether it emits visible light, whether it emits radio, it depends on what chemical you're vibrating. Okay, and the food that we have, they have water in it, and water molecules are like kind of a bird shape, if you want to call it, right? And when they are hot, they kind of vibrate. They do this. That creates microwave in a certain way, but the process is reversible. So if you actually shine water with microwave, if hot water can emit microwave, cold water will become hot when you shine microwave back on it. It will absorb the microwave and become hot. So that's what the microwave, that's how it works. Okay. So in the microwave oven, you put food. Sorry?
Is water conducting the heat, or is
it's just absorbing the light. Think of it like absorbing the light, but the light is not visible light. It's microwave light. Okay. So it absorbs it, it takes in the energy and becomes hot. That's how it works. And when it becomes hot, your food gets cooked. Now here's the thing. If you put food in the microwave that doesn't have a lot of water, it won't become hot enough, because there's not it basically relies on the fact that the food needs water within it to actually become hot. And another thing is that like the food needs to rotate, because there are only some parts where the microwave is absorbed properly and some part is not. So the food, if you notice a microwave oven, there's a plate which turns the food constantly, because there are spots in the microwave like which is more hot and which is not so effective. Now coming back to why a cell phone doesn't work like a microwave. When I say microwave radiation, it's a spectrum. So there's like a lot of frequencies. You can say 10, 20, 30, 40. So if water requires 20, I'm giving an example. If water requires 20 units of frequency, your cell phone is using another frequency, 40 units. Okay. And it's very specific. Okay. These are very fine-tuned frequency, which means if water will become hot at 20 hertz or 20 units, 21 units will not work on water. Neither will 19 units. It's very specific. You need to tune it specifically to heat up water. Okay. And the cell phone and the water, like they use different frequencies. They don't use the same particular frequency. The next thing is that the power that is there in the microwave is about 1,000, 2,000 times more than what your cell phone can emit. And it is confined within that box. Whatever radiation is thrown in the box, it keeps on bouncing around within the box and it doesn't come out. And that's why when you open the door of the microwave, you don't want the microwave radiation to come out, so the microwave stops. Okay, if you open the door of the microwave and the microwave is still being emitted, you are made of water, you will heat up.
Okay.
So there's a fail-safe. There's a fail-safe system that you open the microwave and the microwave shuts down. And it's instant. It's not like a stove where you like switch off the stove, the heat is still dying down slowly. No, microwave shuts down instantly.
There will be some accident, right? And it continues, or it will be a very big accident, right? If something like that were to happen.
I didn't get you, your voice.
No, I'm saying if that fail-safe doesn't work, then it will be a very big accident. You know, it could be fatal.
Yeah. It won't be fatal. I wouldn't say it's fatal, because like the microwave spreads and it goes away. It's not bouncing around in a box, so to say. But it will cause some kind of heating in the water molecule. It might just cause like slight. I've not done it. I've not tried it. I've not checked the experiment around, and I'm honestly not going to try it.
I hope the audience doesn't try to try this at home.
Yeah. Please do not put metal objects within microwave. There's a reason why they do it.
Okay, we
Microwave
have a
oven has
question.
standing wave.
I'll come back to this
I like
metal.
some-
Correct me if I'm wrong. I read somewhere microwave oven has standing waves, hence it cooks food, but cell phones won't have standing waves.
Okay, so when you pluck a guitar string, you will notice that the guitar string kind of bows back and front. That's called a standing wave, and microwave kind of creates that within the box. That's why I said there are some points where it cooks food better than other points, and that's why you need to rotate the food around.
Okay.
Okay, that's because of the standing wave. If you don't rotate the food, like you just put I don't know, cake batter inside and start the microwave, one part of the cake batter will get cooked while the other one will remain uncooked because that part was the point where the microwave was affecting it. It's all because of standing wave, the shape of the wave that creates inside. So yes, cell phones will not create standing wave because, well, it's in the open, it's not confined. The rays which are coming out of the cell phone is just spreading out into space. So standing wave is not created. But even without standing wave, if you open the microwave, and the microwave is still coming out, right? Like there's like constantly, I'm saying, assuming that it's still switched on after you open the door. So you don't really need standing wave for microwave to not affect. At least the effect will be less than what a standing wave can do. But still there will be some kind of effect on you. So it's best that you wait for the microwave to switch off. And if you open the door, the lights don't come on, close the door back and then let the main switch off. So just to be sure.
So Carl,
Yeah.
please tell us what will happen if we put a metal object inside a microwave.
Sparks, lots of sparks, and lightning probably. So what the metal object does is, like, metal is made of a lot of electrons, free electrons. It can move around. It's busy doing its own thing. It's just like kind of swimming in the metal. The electrons are swimming in the metal. But once it gets a microwave, the electron gets enough energy to escape the metal. And if a lot of these get that energy, it's going to like shoot out the metal, creating sparks. Another thing that it does is it can interfere with, like how we have light sources in our house that shines light on us, visible light. There is something called as a magnetron which actually creates microwave inside the microwave oven. Keeping a metal inside can interfere with the way the magnetron works, and it could damage your microwave permanently. Don't put metals inside.
Yeah, that's a caution for all of us. So
Yeah, unless you want to, unless you know what you're doing. Actually, like kids are watching this, and no, kids don't touch the microwave. Let adults handle the microwave.
I think it's best if kids don't touch the microwave, and especially don't put, even for adults like me, I think we should stay away from the microwave. So
I
Heat
have
up
one
food,
question.
yeah. Go ahead.
How does the Wi-Fi work?
oh,
How-
this is an interesting one.
It's the same principle, okay? Like you have radios, cell phones, Bluetooth, and any other communication device, wireless communication device has two objects. You have 2 points. Point A, which is sending the waves, point B, which is receiving the waves. Okay? They have an electronic circuit inside that creates the wave. Now, a Bluetooth will create a certain frequency. The electronic circuit and the design of the circuit, the way it is created, it's to create a certain frequency. The Wi-Fi has a different frequency. Your cell phone network like Vodafone or Airtel or whatever you use, has another frequency. So when you send a Bluetooth file, it uses the Bluetooth network, a Bluetooth circuit, which only another Bluetooth circuit can receive. Okay, when you send a Wi-Fi, you need a Wi-Fi antenna to actually get that. The only difference between cell phone network, Wi-Fi network, and Bluetooth network is the frequency that they work on. All right. So, depending on what frequency you use, you can either transfer data very fast, but your range will become less, and your antenna size will become less. But if you want to transfer data or whatever your communication information to a longer distance, you need to decrease the frequency, which will increase the wavelength, the antenna size. So your Vodafone and Airtel network works on a frequency which can be transmitted over long distance, because it has to go outside your house. It has to go to a telecom cable. There will be a receiver somewhere in your area, but it's quite far away. It's not like inside your house. But if you're using Wi-Fi, you don't have to go that far. So you can increase the frequency, you can increase the speed at which you can transfer data. So that's the only difference. They all work on the same principle, but they use different frequency. And if you use different frequency, then you get different characters of how far you can transfer it, or like how long the information can go and how fast the information can, things like that.
So Carl, another question is that came to my mind just now is we can see stars, but can we also hear stars?
That's a good question. So let me reframe this question. Okay, like if you're an astronaut in space doing a spacewalk, you're not in a satellite, you're not in the International Space Station. You're doing a spacewalk. Okay, your buddies, your colleagues are inside the space station. You are in space doing a spacewalk. What do you think? If he talks, will they be able to hear?
Is there a vacuum in between? So I won't be able to hear.
But they need to communicate, right?
Yeah.
So what they do is they have the helmet, they have a space suit, they have a mic in the space suit. So when you talk, the mic picks up the sound, converts it to electromagnetic waves, light waves, microwaves or whatever, radio waves, any of those waves, which can travel through space. It goes to the space station, which gets converted back to sound, which the people in the space station can hear. So that's how you transfer sound through vacuum. Okay, you cannot transfer sound through vacuum. Now, if you know about stars, it's basically this huge explosion that's constantly going on over there. So it has to be extremely loud. Yeah, so it's going to be extremely loud if you could hear it. But because there's vacuum in between, you can't hear it. Now, what you can do, however, is because the light is fluctuating all the time, you can keep a light sensor and collect all that information, the light information, and pass it through a speaker. Then in some form, you should be able to see the variation of the light in the form of sound. That can be done. You're not hearing the sound, but you're kind of converting the light into something that you can hear. All right. In fact, if you all might have heard about this gravitational wave discovery that happened recently, in order to explain what is happening, they converted whatever information was there into sound, and they called that sound as a chirp because it kind of, the frequency slightly increases. Like, I don't know why they call it a chirp, because a short burst of sound that happens. All right. Yeah. But you can convert one form of information to another using sensors and electronics and stuff like that. All right. So that's what's happening. So you can't hear the explosion, but you can definitely hear the fluctuation of light as sound if you convert the light to sound. All right. So let me see what else I have. Oh, can you just bring up the presentation?
Yeah.
Yeah. So this is a picture which was taken by the Hubble Space Telescope. All right. And if you notice, we are looking at stars. We are looking at a cluster of stars. It's given this name, NGC 6397. I'm not into astronomy, so I'm not sure which part of the sky or what this is. But I know there are stars for sure. But you see these lines which are like going vertically up and down, and there are lines which are going left and right. Yeah. There's also a glow around the star, which is there. Now, also, if someone had asked you to draw a star in school, you would draw this, if you'll notice.
Yeah.
Right? This is the fastest way to draw a star.
Yeah.
The reason why you draw a star like this is because most of the images which were available, they kind of look like this. Okay? And stars are not in this shape. They don't have this cross kind of a shape. The reason why you see this cross kind of a shape is because in the telescope, if you look down the barrel of a telescope, I don't have an image of a telescope, I should have put that. There is a mirror which is supported by these metallic strings or wires, right? And the light tends to interact with this thing. It's saying, you're coming in my way, I'm going to bend around it and I'm going to make this crazy shape. So if a telescope basically has a mirror in the center and it has a wire like that, it's going to give you this cross mark, which is basically what the Hubble Space Telescope actually has. Okay, if a telescope has a shape like this, you have 3 wires in 3 different directions. You'll get the star shape like this over here. Okay, Now, whenever an obstacle comes in front of light, it's going to bend around it. It's going to give you this crazy shape. Now, when light enters your eyes, even your eyes has this iris, or what is it called? That
Retina.
keeps on expanding and contracting. No, not retina.
Irises. Yeah.
Irises. So it has a circular shape and it has an edge. So light actually bends around the edge when the light enters your eye. So if you go during night time and you look at a street lamp, I'm pretty sure you've seen the circle that forms around the street lamp, which doesn't exist. This is because, like the telescope having these lines which is coming the way, these edges, as we like to call them in physics, your iris is creating an edge which this light is bending around and creating the shape. Because your iris is circular, you get this circular shape. Yeah. And as long as your source of light, whatever you're looking at, is like very bright and very tiny, like a point object, you're going to get these circular shapes in your eyes.
Okay.
All right. And I always wondered this. It was really recently, I think so about 2 years back, that I actually found out why this is happening. And I always looked.
So the name for the black part inside your eyes are called the pupils, and the pupils dilate.
Yeah.
Right.
The pupils dilate, right? So yeah. So that's one thing that I actually liked about that, like the way the light bends around objects, and you get these shapes that you don't expect. Like you always see the shapes every time. Even your shadow sometimes blurring. They say about penumbra, umbra, but many a times you will see some weird shapes in the shadow, which is caused by due to the light bending across edges. All right. So I will stop the presentation over here. I don't need the presentation anymore.
Yeah.
Okay. Me. Go ahead.
I'm just putting this time up for viewers to ask us some more questions. If we don't have any more questions, we can close the session for today. So it doesn't look like there are any more questions from our viewers. Thank you, Carl, for giving us such an enlightening talk today. And the questions that we had are being solved. I hope that you come back next time and tell us a little bit more about other phenomena.
Sure, no problem. And I think so, if the viewers actually have questions, they can always ask. Where will they ask it? scienced.com. Or just put it under the video.
So, if the viewers want to know more about our work, we are trying to compile and propagate resources for science, and we would love to help our users to find their interest in science, and all these consequent speakers that are also going to come in the next few sessions. This is not the last. We'll have more speakers like this who will inspire you with real world examples of science, and you all can reach out to us if you have specific interests in any of the subjects in science. Okay, thank you so much, you guys. It was great having you. Thank you, Carl, for taking out this time. And I'll also introduce Linsha to you, who has joined us today. Linsha is the co-founder of Science DB, and both of us is running this platform together. We have some products as well. You can go and check it out on our website. Thanks. Bye.
Bye.